Hello again and welcome. This is going to be a special video. This package just arrived today all the way from Australia. I bet you can guess what's in here. Check it out. Very nice. For some reason, I was thinking this was going to be much larger, and I was not expecting to see this case, I'll tell you that much. Oh, very nice. Very nice. Well, here you go. This is one of 12 of these meters in existence. As I understand it, there's 10 of them that are at Intertech right now being checked. So Dave actually had the other 2, and he graciously sent me this one. Wow, that is thick. Let me clean up the desk here a little bit and grab a couple of meters, give you an idea of how this thing compares size-wise. So here you go. You can see it's a little thicker than what his Brahmin was. You notice the outside dimension is very similar to the BM235. Let's have a look at what else he sent here. Again, I was very surprised to see the case. This is pretty nice. I think this is actually what he's selling with this BM235. Wow. He certainly did not have to send all these accessories. Yeah, so it looks like these are the same cables that are supplied with the 235. Yep, they're identical. Now here's the other thing that he sent. Check this out. So there's 5 400 milliamp fuses and then 2 of the 11 amp fuses. These are all produced by ASTM. So this is the pack he's actually selling. Well, thank you very much for sending these. I'll definitely put these to use. Last set of fuses I actually tried to buy off of Amazon. These were made by UXL, and these are actually a counterfeit SEBA fuse. I did a video on these. So yeah, I actually have a use for these. Well, thank you. I don't know if he shipped this with batteries. Let's just see if it'll turn on. Oh, it does. So I've been corresponding with Dave to try to get a feel for how we want to proceed with this meter. Normally I'll do a fairly detailed review on the meters, and in this case we really can't do that. The problem with this meter is it's not in current production. This is a pre-production unit. It still has not been certified. It's still in the final phases of testing. The firmware is still being developed. So there's functions that this meter is going to have that are not implemented yet. And then there's some features that are not 100% functional. Dave's also said that this meter may not be in calibration. Another thing I normally do is some kind of a teardown video. And I could understand that Dave may be a little sensitive about me tearing this thing apart and giving a detailed analysis of how this thing is designed. While Dave did supply me with the schematics for the meter, I basically agreed that I wouldn't disclose any of that information. The problem with it is because, again, the meter is pre-production, the design could actually change, so they'd like to limit the amount of information that gets released into the public. Makes sense. So before we can do any kind of transient testing, what we have to do is some sort of a functional test. So that's where we're going to start out, is just checking the very basic functionality of the meter, and then we'll start our transient testing. So let's go ahead and get started with that. Let me just show you the contrast adjustment with this. There, that'll work a lot better. So currently I have the meter attached to our 10 volt fluke reference. You can see we are reading roughly 9.997 volts, fairly close. This is with the 1 volt reference. And again, to be clear, Dave has said that this meter may not be in calibration. And I can fully understand that, because the companies that are doing the certification are not going to care about the accuracy of the meter. This is with 1 millivolt applied off of the reference. We'll just change it to the millivolt DC range. We'll just try this with our test box. This will be 60 Hertz. Now this is an AC coupled signal. That appears correct. This is with a DC bias. This is looking at the period, And this is the duty cycle. So that all seems to be functioning. You can see DC, we're at 2.5, that's correct. This should be 0 volts, that's correct. AC, this should be 2.5, that is correct. This should be 2.5, that's correct. Meter has an AC plus DC mode. This should be 3.6, it's fairly close. And this should be 5 volts. Yep, fairly close. So let's just try the temperature. This should be roughly 500 degrees Celsius. Looks pretty good. And let's just see. Should be a little bit over 1,000 and somewhere around room temp. So that appears to be functioning. Let's try resistance mode. This is with a 0.5 ohm resistor. This is with a 1 ohm. This is with 50 ohms. This is with 100 ohms. This is with a 1K ohm. Again, this is a 0.1% resistor. This is with a 10K 1% resistor. This is with a 100K resistor. This is with a 1 meg resistor. Again, this is a 1% part. This is with a 10 meg resistor. This is the continuity test. This is the diode check mode. Again, this is with a short. This is with a single diode. This is with 2 and 3 diodes. This is in capacitance mode, and we're looking at 1 nanofarad. This is 0.1 microfarads. This is with a 1 microfarad. This is with 10 microfarads. This is with 100 microfarads. I don't believe this meter can measure conductance. Yeah, it does not appear to have that feature. Let's just try it with a 100 mega ohm resistor. Yep, it cannot read that. Let's just try the low Z input. So this function does not appear to be working yet. When I go through and transient test the meter, we're still going to be selecting this position of the switch. The only thing we can show is the backlight. That seems to be functioning. So the previous meter I had tested before the 121GW was this Gaussian Metrowatt MetroHit Ultra. And what I had discovered was the meter was highly sensitive to outside fields. I could actually ground the 2 inputs of the meter and then wave my hand around this thing, and it would affect the readings when the meter was in its 300 millivolt range. I also discovered I could take this piece of felt cloth, rub it against my hair, and then bring this near the meter, and that would really cause the meter to vary quite a bit. So I thought for fun, let's just try that with the 121GW. So again, I'm just going to attach this shorting strap to the input of the meter. We're going to set this to its most sensitive range. You can see it's reading out in the millivolt DC right now. And I just move my hand by the meter. This would cause that Gaussian to wander all over the place. Actually, you could not clear the meter out. So if I'd hit the rel on it, by the time I pressed the rel, the meter would be off several hundred microvolts. So let me just charge this thing up. And you can see it has no effect on this whatsoever. And you wouldn't expect it would. You know, I've never seen anything like that until I tested that Gaussian. That meter just has a lot of design issues. So there you go, a pre-production meter actually outperforming the high-end Gaussian in a test. Another thing I like to do is just take my RF generator. I've got a small antenna and I just sweep this by the meter, and I just basically check to see if there's some kind of a gross sensitivity problem with the meters. If you watch the last review I did of the Gaussian Metrowatt, I had actually taken that meter along with a few other ones and placed those inside of an RF chamber, and we ran them at 10 volts per meter. And I did that just to give you some kind of a sense on how sensitive the Gaussian was. You can see there's something going on. I'll just move the antenna away. You can see there's a difference of about 18 microvolts or so. Kind of makes sense. It's more sensitive off of this lower right near the input. So that's currently at 793 megahertz. Here you can see it's actually increasing by about 41 microvolts. This is at roughly 745 megahertz. This is at roughly 342 megahertz. You can see this is definitely another area that it's sensitive to. All in all though, it looks pretty decent. I've seen some meters that were very sensitive with RF. So off to the left you can see we have our high voltage power supply, and this is attached to the EEVBLOG BM235 along with the 121 GW. What we're going to be doing is applying a high voltage DC signal to both meters, and let's just see if this meter breaks down at all. So you can see right at 600 volts. So that's the 121 GW that's beeping. So it's giving us some kind of an indication of an over range. We'll just continue on up. So right at 660 volts we'll get this over range. And this is the limit of my power supply, so 983 volts. So I've gone ahead and restrapped our power supply to output an AC voltage. And again, the two meters are in parallel. You can see we're outputting roughly 540 volts. And again, this is roughly at 60 hertz right now. And there should be no DC offset, or very minimal, so you can see it's less than a half a volt. This is AC plus DC, so that seems correct. And of course the DC again should be basically 0 volts. So that all seems fine. So what I'm going to do is change the DC bias to this. So there's a negative 400 volts of DC bias on top of our AC. And let's try going the other way with it. This is roughly 400 volts positive of DC bias. Again, the 121 GW is not having any trouble with this. So this next test is based off of something I see Dave Jones doing a lot of his multimeter reviews. You'll basically take the meter and attach it to their AC power and then rotate the knob through all its different functions. In this case, this transient generator will put out a 220 volt full rectified signal, and it has a current limit built into it. So instead of having the meter attached directly across the line with no protection whatsoever, this will limit the current to, I think I've got a program right now, to about 500 milliamps or something. And basically if the meter overcurrents this will just shut it down. So if we attach the inputs, and we'll just select our low Z input. Well, that's interesting. You may remember this low Z wasn't reading right before. Huh. Well, this is very strange. So, if it's in the low Z input, and I attach it so the output of the transient generator is essentially going negative, you can see it's reading in AC volts. If I flip the two, you can see it changes over to DC. So both of the numbers that's actually reading are correct. We can see that with Dave's other meter. If I just reattach this, there's your 112 volts. And in DC, there's your 240 volts. So again, this meter is pre-production, so I'm assuming that they're going to have some quirks like this. Anyway, so let's go to DC volt mode. And you can see that's correct. So what I'll do now is just rotate the knob through the rest of the functions. So let me go ahead and I'll functional test the meter and let's see if there's any problems with it. Alright, so our 121 GW survived that test just fine. So looking back at the data that I've collected from the meters that I've tested, again, this spreadsheet's available online for free. You can just download it. The meters that had failed that 220 volt test were the Tech Power TP2844R, the Unity UT20B, the TPI Summit TPI194-2, that's the funky fluorescent yellow meter, and also the Maztec MS8211. So the next test I'd like to do is a static discharge, and we're going to be using this small grill starter for that test. So I've made a video where I characterize the output of this, and this is nowhere near what the IEC standard requires. While it does put out a higher voltage, the output current on it is very low. But it has damaged quite a few meters. As a matter of fact, it damaged this UT181A on the left with just one strike. It wiped out the whole power supply on it. And again, that shows the importance of the circuit board layout design. And again, I've tested other Unities that have failed this test. For the UT61E, I actually did a series of videos where I modified it to try to improve the robustness, and I was able to get that meter to survive this test. The same thing with the UT181A. I've actually gone in and modified the circuit board layout on this, and this meter is easily able to survive this along with pretty much any other transient I've been able to generate. So you can see I have our grill starter out. We're going to be applying 5 transients, both positive and negative, in each mode of the meter. These will be a direct contact discharge. And again, I don't do anything with the current inputs. Alright, that's it. We'll go ahead and functional test it. So I know my box can't drive it in the low Z mode. Let's just see. So 110 volts AC. You notice that I flipped the polarity and now it's reading it in AC volts. Instead, before it was backwards of this. I'm not sure what's going on there. It's pretty funny. Oh, and this time it's staying in AC volts. Very strange. Huh. Look at this. Before, this would be in DC. Oh, this time it switched. Alright, so anyway, it looks like that mode works fine. Like I say, this meter's just got a few quirks yet, but it's not released for production, and they have a little bit more work left to go. So this will be DC volts mode. This should be 5. This should be 2.5. Try the AC volts mode. This is capacitive coupled, 2.5. That's correct. Direct coupled, 2.5. That's correct. This should be roughly 115 millivolts. That's correct. This should be roughly 500 degrees. That's correct. And this should be roughly 60 hertz. That looks fine. This should be 60 as well. That's fine. And this is again with 60 hertz. And this is looking at the period. That's fine. And this would be duty cycle, so that's fine. This is with an open. That appears fine. This is with 50 ohms, 100 ohms, 1K, 10K, 100K, 1 meg, and 10 megs. This is continuity test. That seems fine. Again, here's a single diode. This is with 1 nanofarads. This is with a 0.1 microfarad. This is our 1 microfarad, our 10 microfarads, and this is with the 100 microfarad. So it looks like the meter survives our grill starter just fine. Again, looking at the data that I've collected so far, meters that had failed that test were the Unity UT61D, the UT61E, the X-Tech EX430, the Vichy VC99, and the Unity UT181A. Those were all damaged by this grill starter. So for the next test, we're going to be using our homemade ESD gun. This will actually put out something very similar to what the IEC standard calls for. And again, we're going to be applying those transients directly to the inputs of the meter. Again, so we'll be applying 5 transients, both positive and negative, in each mode of the meter. That's it. Let me go ahead and functional test it. So I functional tested the meter, and it looks like it survived that ESD discharge test just fine. You can see we have our transient generator powered up. It's currently set for 1000 volts per division. Normally I'd be using our LaCroix scope, but today, because of the heat, I'm just going to be using this battery powered Fluke 97. Contrast on this is a little tough to see, but this is currently set for 500 volts per division. It's shown up here as 50 millivolts. I've selected it as a 1-to-1 probe instead of a 10,000 to 1. It's also set for 50 microseconds per division. This is currently our peak height, and you can see we're set at 1 kilovolts. So we'll be applying 5 transients, both positive and negative, with the meter set to each function. And this first transient will be 1000 volts peak with a 100 microsecond full width half height and a 2 ohm source impedance. And that's it. So the meter passed functional test just fine. I've reset the generator for 1.5 kV. Again, this will be 100 microsecond full width half height with a 2 ohm source impedance. And again, this will be 5 transients, both positive and negative. Okay, that's it. We'll go ahead and functional test the meter. Alright, the meter passes functional just fine. I've reset the generator for 2000 volts peak. One thing I should mention is that these tests really have nothing to do with the surge rating for the meter. So these meters will all have a CAT rating. This one happens to be rated for CAT 3 600 volts. What I'm trying to do with these tests is to find out just how robust the meter's front end designs are. This generator really doesn't put out a whole lot of energy. It's about maybe 20 joules on the high side. What I'm doing with this generator is basically following the same voltage profile, except I'm doubling the full width half height, and then the current profile I don't really concern myself with. Again, I'm not trying to explode the meters. I'm just trying to find out how weak the front ends are. Alright, so again, this will be 2000 volts peak, 100 microsecond full width half height with a 2 ohm source, and this will be 5 transients in each mode of the meter again. And that's kind of what it looks like with the scope. So that shows up. Alright, that's it. I'll go ahead and functional test it. If we look at the spreadsheet, you can see quite a few meters have failed at this level and lower. At 2000 volts, the Klein Tools MM2000 had failed. Looks like that's the only one. At 1.5 kV, it looks like the Amprobe AM530 had failed, along with the Tech Power TP40, the Fluke 87V, the Victor VC921, and the Maztec MS8211D. And then at 1000 volts, it looks like the BK Precision 2705B had failed, along with the Circuit Test DMR 6550, the UTL DM2, the Southwire 12070T, the Innova 3320, and then the Woods DMM W3. So by 2000 volts, it looks like quite a few of the meters have failed. Unfortunately, it looks like we have also damaged Dave's meter. So I just started to go through it. Let's just go through it together here. So again, I'll turn on the AC from the transient generator. You can see it's reading roughly 108 volts. And I'm assuming if I flip this, maybe we'll get it to read DC this time. There you go, DC 240. So that mode seems alright. I'll go ahead and turn off the transient generator. I think we're done with it. See, I'm just going to be using our box from here on out. So with 5 volts DC applied, you can see the meter is reading that just fine. Flip the leads around to the correct polarity. So there's our 5 volts. And in AC mode, this should read 2.5. And this should read 2.5 as well. Try AC plus DC, so again this should read roughly 5 volts. That's correct. This should read 2.5. That's correct, and this should be 2.6. And that's correct. In the millivolt range, this should be roughly 115 millivolts. And you can see it's reading quite low now. So let's try the temperature mode. This should be roughly 500 degrees Celsius. And we can see that that no longer works. It's almost like a gain problem. So again, on the box here I can set it basically from 27-ish or so degrees up to about 140. You see when I turn it all the way down, it was reading 27 degrees. It's now reading roughly 38. And here it's already at over range. You can see it's like there's a huge gain change now. This would normally read 500 degrees. See, for the frequency, this should read 60 Hertz. That's correct. This should be 60 Hertz as well. That seems fine. That is correct. That's the period. And the duty cycle, that seems fine. Alright, so let's try resistance. This is a open circuit. That seems fine. This is with 0.5 ohms. This is a 1 ohm. This is 50 ohms, 100 ohms. You can see they're all reading off by quite a bit. This will be 1K. Wow, look at the error now. 2.7K for a 1K. This is a 10K. You can see it's reading 358. This is with a 100K. And you can see it's now overranged. This will be a 1 meg and a 10 meg, so all overranged. Continuity test, that appears to work. Diode check, so again this is an open. This is with a short. Let's just try it with a single diode. That's correct. Here's with 2 diodes, and that is correct. And here's with 3 diodes, and that is correct. So in capacitance mode, with the leads open, this would normally be reading 0. You can see it's hunting. I don't know, we can attach something. This is a 0.1 microfarad. And you can see it cannot find the correct value. So it looks like we've damaged the meter at 2000 volts with a 100 microsecond full width half height and a 2 ohm source impedance. So unfortunately, I think that's going to be it for the video. There's not much else I could do. I could attempt to go in and try to analyze the meter. Unfortunately, I don't think I can make that information publicly available. I'd like to take this time again to thank Dave for making this meter available to us. Again, there was only 12 of these in existence. He had 2 of them. He offered to send this one specifically to be transient tested, and hopefully he's learned something from this. Again, to be clear, this isn't something that David actually paid me to do. He did send me the meter for free, and you know, like I say, along with some very nice accessories and some fuses. So I'm thankful for all that. Other than that, it's not like there was any cash that changed hands. I'm just doing this out of my own interest. I'd also like to welcome all you new followers. Glad to have you on board. Well, I think that's going to be it. Until the next meter. Later.